Today I'm going to prove that an invertible matrix times an invertible matrix must equal an invertible matrix. And without further ado, let me begin with my assumptions. So let's say A and B are invertible matrices, are invertible matrices, all right? And let's say, or I'm going to make a proposition here that all invertible matrices are independent. Are independent matrices, all right? Hopefully you know what it means for a matrix to be independent, all right? And let's get into the proof. So I'm going to do a proof by contradiction. So let's say C is dependent or not invertible. Let's say C is dependent, non-invertible. This would mean if we were to split up C into multiple columns. So let's call this C1, C2, dot, 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 dot. So C1 will represent one whole column, all right? This means that there is some, or no, there's some C3 for which the linear combinations of U times C1 plus V C2 equals C3. And you can prove this for longer chains, but I just want to prove it for this short chain, all right? So there's some column which equals a linear combination of the other columns, all right? So what does that mean? Okay, and U and V are scalars here, right? They're usually used as vectors, but I'm using them as scalars. So this means that, oh, what does C1 equal? Well, we also can write C1 as AB1. We can write C2 as AB2. We can write C3 as AB3. Why? Well, you can just look how matrices operates. So let's say we have matrix A. We need to multiply by multiple columns by B1, B2, B3, etc. So when we multiply B1 column to A, this would be transferred. So let's just take into consideration AB1. This would simply be C1 if you just think about it. Because we can partition these into multiple columns, which in the end, after A times B1, would be the partition of the C columns. Yeah, I don't know how to explain much. You just have to think for this for yourself. We can just, disregard everything else here. We multiply B1 to A, and then that would be equal to the first column here. That would be equal to C1. And then we can just do the same thing for the next column. So AB2 would equal C2, right? Because that's simply how matrices work. So we know this to be true. Now, if this is the case, we can say that, look at this formula here. We substitute everything. So AB3 equal U AB1 plus V AB2. And one of the assumptions we made were that A is invertible. So we can just invert A, multiply A to -1 to each one of these terms. So here's what we get. B3 equals UB1 plus VB2. And we get a contradiction. This would say, therefore, B is dependent because a column in B3 is a linear combination of the other columns in B. Therefore, B is dependent. But we assume that B is invertible and therefore independent. So therefore, C cannot be non-invertible. That means it must be invertible. And that's the proof. I think the hardest part to grasp about this proof is that AB1, we can partition these columns. Or you just need to, try it yourself and you'll see it's straight that AB1 would equal C1 in this column, AB2 would equal C2 in that column. All right, and you might argue that, hey, what if it equals some GC3 or GC4 plus FC5? Well, yeah, you can do this, but to simplify it, I only chose two terms, like a linear combination of two terms. All right, and that's my proof. Thank you.